uncertain about your uncertainties. If your brain feels like this meme every time you see a plus-minus sign in a physics paper, trust me, you are not alone. Most students treat uncertainties like a guessing game, but this topic is a goldmine for easy marks. If you know the logic behind the math, I've pulled out the 4 most dangerous uncertainty questions they've asked so far. These aren't just textbook problems. These are the actual grade killers from this year's exams. Whether it's calculating the thickness of a glass tube or the complex density of a liquid in a beaker, the exam board loves to set traps. But today, the guessing stops. I'm going to give you the 3 core rules that make these questions impossible to get wrong. Once you have these 3 keys in your pocket, we're going to go through these 25 questions together and crush them in seconds. Rule number 1 is the most common trap in calculating uncertainties. When you are adding or subtracting two values like finding the change in temperature or the thickness of a wall, you always add the absolute uncertainties. Think about it. If your first measurement is slightly off and your second measurement is also slightly off, the total error in your result has to be bigger, not smaller. Subtraction does not cancel out your mistakes, it doubles them. In physics, errors only ever accumulate. Rule number 2. When you are multiplying or dividing, we stop looking at absolute numbers and start looking at percentages. If you're calculating density, you take the percentage uncertainty of the mass and add it to the percentage uncertainty of the volume. Even though you are dividing the values, you are adding the errors. This is the only way to find the total relative slack in your final answer. Rule number 3 is the grade maker. When a variable has a power, like v squared in kinetic energy or L cubed in the volume of a cube, that power acts as a multiplier for your uncertainty. If your length has a 2% error and you cube it to find volume, your volume now has a 6% error. The power rule is the reason why small errors in a diameter become massive errors in a volume. Respect the power, or it will break your calculation. 3 core rules. That's all the things you need. Now, let's go into the 2025 papers and use these rules to crush those for multiple choice questions. First up, question 1 from paper 14. We're using calipers to find the wall thickness of this glass tube. Now, look at the measurements. The external diameter is 12 plus or minus 0.1 millimeters, and the internal is 10 plus or minus 0.1 millimeters. To find the thickness, we subtract the internal radius from the external radius. Here is the trap. Most students subtract the diameters to get 2 millimeters, and then they subtract the uncertainties to get 0. Never do this. Remember rule 1. Even though we are subtracting the values, we add the absolute uncertainties. So 0.1 plus 0.1 gives us a total uncertainty of 0.2 for the diameter, and we divide it by 2 to get the uncertainty of the thickness of the wall. The correct answer is A. If you chose B, you forgot to divide the uncertainty by 2. If you chose D, you forgot to divide at all. Stick to the rule, and you're safe. Moving on to level 2 from paper 12. We need the percentage uncertainty in the density of a steel cube. This question is a double-header. We have division and a power. Density is mass over volume, and for a cube, volume is the cube of length. Recall the second and the third rule. The percentage uncertainties in mass and length are needed. Because the length is cubed, we must triple its percentage uncertainty. Percentage uncertainty for mass is 10 divided by 975 times 100%, roughly 1%. For length, it's 1 divided by 50 times 100%, which is exactly 2%. With the power 3 as the multiplier, the uncertainty becomes 6%. After adding up the percentage uncertainties, it gives a total of 7%. The answer is B. Notice how the 2% error in length became the dominant factor because of that power of 3. Level 3, paper 11. This one is tricky because it asks for the absolute uncertainty in volume. But we have to use percentage rules to get there. First of all, volume of ball is 4 over 3 pi r cube. Again, we apply rule number 3. The power of 3 on radius becomes a multiplier to the uncertainty of radius. So, the percentage uncertainty is 0.02 divided by 5.26 times 100%. With the power 3 as the multiplier, the percentage uncertainty is 1.14%. For the final step, we find 1.14% of the actual volume, which is for over 3 times pi times half of the diameter cubed times 1.14%. The volume is 76.2 centimeters cubed and 1.14% of this volume is 0.87 centimeters cubed. That gives us answer B. This is a classic public exam question as it forces you to switch between absolute and percentage values twice. Finally, the boss level from the paper 12. This looks intimidating, but it's just rule 2 and 3 combined. We need the percentage uncertainty and density. The formula for density is mass over volume, and the volume of the liquid in the beaker is a cylinder, which is pi r squared times h. We apply rule number 2 and add up all the percentage uncertainties. Don't forget the multiplier for the percentage uncertainty of the radius, as there is a power of 2 in the formula. Now just add the chain. 10% plus 2 times 3% plus 2% gives 80%. The answer is D. You just solved the hardest uncertainty question in the 2025 series in under 30 seconds. And there you have it, for real questions from the 2025 series solved using just 3 golden rules. Physics can feel like a guessing game, but it doesn't have to be. If this video helped you feel a little more certain about your uncertainties, hit that like button and subscribe to MathVis Mastery for more 9702. Drop a comment below if there's a specific paper or topic you want me to tackle next. Good luck with your revision, and I'll see you in the next one.